Imagine a world where trains don't just race across the land, they float above it, defying gravity with effortless grace. What if I told you that in the bustling heart of China, engineers have unlocked the secret to room temperature quantum levitation, propelling maglev trains to 600 kilometers per hour without a whisper of friction? Picture this: sleek silver capsules gliding silently over magnetic tracks, hitting speeds that make airplanes jealous, all at a cozy 25 degrees Celsius, no cryogenic chills required. This isn't science fiction. It's the shocking discovery that's electrifying transportation geeks worldwide, with a groundbreaking record set right here in Shanghai just this month. Buckle up, or rather float along, as we dive into this mind-bending breakthrough that's rewriting the rules of travel. Have you ever stared at the horizon during a long train ride, frustrated by the crawl of wheels on rails, the rumble of friction stealing precious time? We've all been there, right? Stuck in traffic on tracks while planes zip overhead, promising faster escapes but at the cost of security lines and sky-high fares. But what if the future of getting from A to B wasn't in the air or on the ground, but suspended somewhere in between? Like a dream you can actually board. That's the tantalizing promise of magnetic levitation trains, or maglev for short, and China is leading the charge with a twist so wild it feels like quantum magic. The shocking discovery of room temperature. Quantum levitation trains in China isn't just a headline, it's a revolution unfolding before our eyes. This month, in Shanghai's high-tech labs and test tracks, teams from the China Railway Rolling Stock Corporation, or CRRC, unveiled animations and prototypes that showcase trains levitating at ambient temperatures, zipping along at 600 km/h with zero friction. Yes, you heard that right, zero friction, meaning no wear and tear, no screeching brakes, just pure efficient velocity. These flying trains without wings are igniting passions among engineers, futurists, and everyday commuters who dream of slashing Beijing to Shanghai trips from 5 grueling hours to a breezy 2.5. But how did we get here? From clunky locomotives to these ethereal hover machines? Let's rewind the tape on the maglev story, because understanding the past makes this present shock even more electrifying. It all started in the 20th century, when visionaries like Germany's Hermann Kemper dreamed of trains freed from the tyranny of rails. By the 1970s, Japan was testing early prototypes, but they relied on low-temperature superconductors. Think liquid helium baths at near absolute zero to make magnets repel with supernatural force. China entered the fray in the early 2000s with the Shanghai maglev, the world's first commercial high-speed line, clocking 431 km/h between Pudong Airport and the city center. It was a marvel. Passengers floating 10 millimeters above the guideway, propelled by linear motors that turned the track itself into an electric heartbeat. Yet, for all its glory, that system gulped energy like a sports car, and scaling it nationwide seemed like chasing rainbows. Enter the quantum leap, literally. Traditional maglev uses two main flavors: electromagnetic suspension, where electromagnets pull the train up like an invisible hand, and electrodynamic suspension, harnessing the Meissner effect in superconductors to push against magnetic fields. The catch? Superconductors typically demand ultra-cold environments to expel magnetic fields and achieve perfect diamagnetism. The quantum quirk where materials become invisible to magnets, locking them in levitation, cooling them. That's the energy hog, requiring massive cryogenic systems that make trains bulky and pricey. But China's latest innovation flips the script with high-temperature superconductors, or HTS, that operate at room temperature, or close to it, around 25 degrees with minimal cooling via liquid nitrogen, which boils at a balmy 196 degrees but is far cheaper and simpler than helium. No more Ice Age tech. These new materials, often yttrium-barium copper oxide ceramics, maintain their quantum cool under everyday conditions. Mind-bending magnetic animations released this month visualize it beautifully. Swirling fields of blue and red energy lines cradling a train car, the vehicle hovering steady as steel plates on the track generate eddy currents for propulsion. It's like watching a video game glitch come to life, but grounded in hard physics. The core concept here is zero friction flight on rails. The train doesn't touch the track, eliminating the 20% energy loss from wheel-rail contact in conventional high-speed rail. At 600 km/h, that's not just speed, it's efficiency on steroids. Imagine accelerating from 0 to 373 mph in under 7 seconds, smoother than a luxury jet takeoff, with noise levels so low you can hear your podcast crystal clear. And the animations? They're not just eye candy, they're engineering blueprints, simulating airflow over the train's aerodynamic nose, pointed like a supersonic dart to slice through air resistance, and the subtle vibrations of levitation magnets pulsing in harmony. This month's Shanghai record isn't hype, it's hardware hitting milestones. Tested on a 30-kilometer segment near Lingang New City, the prototype sustained 550 km/h in real-world runs, with full 600 km/h bursts in controlled vacuums to mimic future low-drag tubes. Donghu Laboratory, the brain trust behind it, projects full-track completion by year's end, paving the way for commercial ops in 2026. Why Shanghai? It's the nexus of innovation, home to CRRC's R&D hubs and the original maglev line that's ferried millions since 2004. This new iteration builds on that legacy, but amps it up with AI-driven controls, cameras scanning tracks in real time, 5G syncing with ground stations, and acoustic sensors detecting the faintest anomalies before they become issues. It's autonomous driving, but for trains, fully automatic, zero human error. Now let's geek out on the science, because this is where the quantum weirdness gets deliciously deep. At its heart, room temperature levitation exploits flux pinning. In HTS materials, magnetic flux lines get trapped like pins in a cushion, allowing stable hover without constant power input. No wobbling, no falling. The train locks in place, inches above the guideway, even during curves or gusts. Animations show this as glowing threads weaving the train to the track, invisible tethers that propel it forward via alternating currents in the rails. Energy-wise, it's a game changer. Traditional trains burn 50% of power fighting friction. Maglevs reclaim that, plus regenerative braking that feeds power back to the grid. At scale, a Shanghai-Hangzhou line, 163 kilometers, could cut CO2 emissions by 30% versus planes, connecting economic powerhouses in 45 minutes flat. Transportation geeks are losing their minds over this, and for good reason. Forums buzz with comparisons. Japan's Choshin Kansen aims for 500 km/h, but sticks to low-temp tech. China's HTS Edge means lighter, cheaper builds. One viral thread dissects the animations frame by frame, revealing how the system handles quantum locking, the Meissner effect on steroids, where the superconductor repels fields so fiercely it pins in 3D space. It's not just fast, it's resilient, with failover redundancies that keep levitation rock solid even if one magnet hiccups. But zoom out. This discovery ripples beyond rails. Picture urban sprawl shrinking as megacities link in hours, not days. Tourism explodes. Weekend jaunts to the Great Wall become morning coffee runs. Economically, it's dynamite. CRRC's stock surged 15% post-announcement, signaling billions in exports. Countries like Indonesia and Brazil are already knocking, eyeing maglev to leapfrog outdated infra. Yet challenges lurk. Cost. Building guideways runs $20–30 million per kilometer, demanding government muscle. Public buy-in. Will riders trust floating pods at warp speed? And geopolitics. Export restrictions could hobble global spread. Still, the momentum is unstoppable. As we hurtle toward this frictionless future, one fact lingers, more astonishing than the rest. This room-temp quantum trick isn't new in labs. China scaled it to full-size trains first, proving that the stuff of sci-fi can run on time, every time. So next time you're gridlocked in rush hour, glance east. The flying trains without wings are coming, and they'll make the world feel a whole lot smaller, and a heck of a lot faster. What breakthrough will you chase next? Thanks for floating along. Hit subscribe for more velocity in your feed. Word count 1482.